Section 9.6 is the ratio and root test. In this section, we're going to learn the last two tests that we can use to determine if a series converges or diverges. Let's start by looking at the ratio test. The ratio test says, let the sum from n equal 1 to infinity of a sub n be a series of non-zero positive terms. Then, the series converges absolutely if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. The series diverges if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is greater than 1, or if that limit is equal to infinity. And finally, the test is inconclusive if that limit, the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, is equal to 1. So when we take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, you have three possibilities. You have a number that's less than 1, and that means you converge absolutely. You have a number that's either greater than 1 or infinity, and that means that you diverge. Or you're equal to 1, which means the test is inconclusive, or that test fails. You have to try a different test. Now, the ratio test is great for any kind of series with a factorial, or a series that has a mix of polynomials and exponentials. So anytime you see a factorial in your series, you're going to want to use the ratio test, or if you see a mix of polynomials and exponentials, you're going to want to use the ratio test. For example, number 1 has a factorial, and you know you'd want to use the ratio test for that. Number 2 is a mix of polynomials and exponentials, so you'd want to use the ratio test when you're trying to determine if these series converge or diverge. So let's determine the convergence or divergence of the series, and we're going to use the ratio test on these. Example 1 is the sum from n equal 1 to infinity of 1 over n factorial. The ratio test says that I need to look at the limit as n goes to infinity of the absolute value of a sub n plus 1. Well, if this here is my a sub n plus 1 would be 1 over, instead of n I'd write n plus 1 factorial. And then that gets divided by a sub n, so divided by 1 over n factorial. But we're dividing by a fraction. Instead of dividing by a fraction, we're going to multiply by the reciprocal. So the limit as n goes to infinity of the absolute value of 1 over n plus 1 factorial times the reciprocal, which is n factorial over 1. Now most times I'm going to skip to this step right here, since we'll be dividing by fractions and it's easier to just multiply by the reciprocal. Once we're here, we look at these factorials and we know we need to simplify them. Recall, when you're simplifying factorials, figure out which one is bigger. Well, n plus 1 factorial is bigger than n factorial. That is the one that we need to expand then. So we say that this is equal to the limit as n goes to infinity of the absolute value of 1 over. When I'm expanding n plus 1 factorial, that's just going to be n plus 1 times n factorial, and then times n factorial over 1. Notice now that your n factorials will cancel, and you're just left with the limit as n goes to infinity of 1 over n plus 1. Well, what's the limit as n goes to infinity of 1 over n plus 1? Well, it's 1 over infinity, and we know that that is equal to 0. Well, 0 is a number that is less than 1, and whenever you end up with something that's less than 1 when you're taking that limit, your series converges absolutely. Therefore, we say that by the ratio test, our series converges absolutely. And we say converges absolutely because the ratio test has us taking the absolute value. Let's look at number 2, the sum from n equal 1 to infinity of n squared times 2 to the n all over 3 to the n. To use the ratio test, we need to take the limit as n goes to infinity of the absolute value of a sub n plus 1, this is a sub n, so a sub n plus 1 would be n plus 1 squared, and then times 2 to the n plus 1, all over 3 to the n plus 1. And then instead of dividing by a sub n, I'm going to multiply by the reciprocal. If I multiply by the reciprocal, I have 3 to the n over n squared times 2 to the n. Now I'm going to expand where I can, and I'm also going to group things together. This is polynomial and this is polynomial. I'm going to write those together. This is 2 to a power and this is 2 to a power. I'm going to write those together. 3 to a power and 3 to a power. I'm going to write those together. So we're looking at the limit as n goes to infinity of n plus 1 squared over n squared times, I'm going to expand 2 to the n plus 1. Recall, if you have x to the m plus n, that's equal to x to the m times x to the n. So if you're adding here, you can split it up over multiplication. 2 to the n plus 1 becomes 2 to the n times 2 to the first. And that's all over 2 to the n. And then times, and then 3 to the n, all over, and that expands to 3 to the n times 3 to the first. Now let's cancel. I notice that I can cancel a 2 to the n, and I can cancel a 3 to the n. So I'm left with the limit as n goes to infinity of the absolute value. Well, notice right here, I'm raising both my numerator and denominator to the second power. So I can rewrite this as the whole fraction, n plus 1 over n, raised to the second power. And this is going to be times, well, that's just 2/3. Now you can split up limits over multiplication. You can also rewrite this portion of the limit because it's a composite function. We could rewrite it as the limit as n goes to infinity of the absolute value of n plus 1 over n quantity squared. Again, this is a composite function. It's something squared, so we could rewrite it as the limit of the inside quantity squared. And then if we're taking the limit as n goes to infinity of a constant, we know that that's just going to be the constant. Now I have the limit as n goes to infinity of the absolute value of n plus 1 over n quantity squared times 2/3. Well, this is a power of n over a power of n. If I were to reduce that, that's just going to be the limit as n goes to infinity of 1 squared. Well, the limit as n goes to infinity of 1 is going to be 1, and 1 squared we know is equal to 1, therefore this is equal to 2/3. Well, 2/3 is a number that's less than 1, therefore we know that by the ratio test, our series converges absolutely.